All right, we'll take a look at section 3.5 in this lesson, limits at infinity. And this is getting at, what happens to the y value of a function? What does f of x do as x itself goes way out to the left or right, if it's going out to negative or positive infinity? Okay, so that's what's meant at limits at infinity. So to get into it, let's kind of take a look at the graph of f of x equals 1 over x. Okay, it's a pretty straightforward hyperbola here. Sketch it out. And more or less is going to look like this. Get this section in the first quadrant. Get this region in the third quadrant. Okay. And we do have some asymptotes here. We have a vertical asymptote along the y-axis. Or the line x equals 0, we could call that. And we have a horizontal asymptote at the y value of 0 on the x-axis. Okay, so let's take a look at a couple of things. All right, so first up, let's actually take a look at the limit as x approaches 0 of this function. Okay, algebraically, what are we going to get back? We're going to get back 1 over 0. The fact that we have 0 in the denominator only tells us we have a vertical asymptote. And we can certainly verify that by looking at our graph. Yes, we do have a vertical asymptote at the x value of 0. Just as an algebraic reminder, if you get back 0 in the denominator only, you got to try to remember to test the left and right-handed limits. And again, algebraically, we're going to get back 1 over 0. Coming from the left, the 1 in the numerator is positive. The 0 down here, we're not actually at 0. We're almost to 0. Coming from the left, that's going to be a negative value. So the sign of this fraction as a whole is negative. So again, that's an algebraic way to determine we're going to negative infinity from that side. Coming in from the right, we have a positive 1 in the numerator. Once again, we're getting close to 0 from values just above 0. So the denominator will be some very small positive number. And a positive over a positive takes us off to positive infinity. So again, we can verify that with the graph. Yes, as we come into 0 from the left, we do shoot way up to positive infinity. As we get close to the x value of 0 from the from the right, we go up to positive infinity. From the left, we go down to negative infinity, okay? So again, the algebra and the geometry should come together here, and we see all this, okay? So that's a little bit of review of vertical asymptotes, part A. Part B, let's actually take a look now at what happens as x goes way out to the left or right. So to go way out to the left, we're actually looking at what happens as x approaches negative infinity. Okay? Well, visually we can see what's going on here. As the x value continues to the left, what is this thing going to get closer and closer to but never touch? Our horizontal asymptote. Okay? So this function is going to keep getting closer and closer and closer to that value where the blue line is. It's never going to touch it. What is that value going to get closer and closer to? Well, the y value of 0. So we can see that if we go way out to the left, that y value is just going to get closer and closer and closer to 0 from underneath. Okay? And if we look at what happens as x goes way out to the right, we're looking at what happens as x goes to positive infinity. Well, again, as we look at this, we can see what's happening geometrically. The further out to the right we go, the closer and closer the purple function is going to get to the blue asymptote, which again is at a y value of 0. Okay? So in either case here, for parts B and C, we can see that as x goes left or right, we approach a y value of 0. Okay, and that's kind of our first example of limits at infinity. Okay, we did this one kind of geometrical. Okay, but what we're going to want to do is kind of understand algebraically how to do this as well. Okay, so I mean, think about what's going on here. If I actually plug numbers in for x getting bigger and bigger in the negative direction, like let's say I plug -1 in first, getting bigger in the negative direction, so -10, -100. -1000. Well, what's going on with these fractions? I mean, these denominators are getting bigger and bigger and bigger. What do these fractions actually equal? That's -1, -0.1, -0.01, -0.001, and so on. I mean, think about what's actually happening to these values. They are indeed approaching 0, right? So kind of the thing that's going on here is that the denominator is getting larger and larger and larger. Okay, the numerator is relatively staying put at 1, but the denominator is what's getting bigger and bigger and bigger. And the bigger the denominator is, what effect is that going to have on the overall fraction? These things get smaller and smaller and approach 0. Okay? And the same thing happens as we go off in the positive direction. I'll start at 1, I'll make the denominator bigger in the positive direction, and you should be able to see what's happening to the overall value of the fraction here. Again, these things are getting closer and closer to 0. Okay? So whether we're getting closer to 0 from below the x-axis or above the x-axis, either way, when the denominator gets really big compared to the numerator, okay, the limit will approach 0. Okay, so let's kind of summarize this with a fact. Okay, I'll write it like this. The limit as x approaches positive or negative infinity of c over x to some power n, okay, is always going to equal 0. Okay, c up top is some constant. N is some number greater than or equal to 1 down in the denominator. All right. Actually, I don't even think it needs to be greater than or equal to 1, to be honest with you. Okay, N is just some constant in the denominator. Okay, but the idea is this. Look, if we have some fraction where the denominator is going to be getting bigger and bigger and bigger, this thing is going to approach 0. Okay, and believe it or not, this little fact here can kind of is going to kind of be what we build off of as we talk about, you know, different cases when x approaches infinity. Okay, so let's go through a couple examples. We're going to do them algebraically to start, and then we're going to do them more analytically. Okay, so let's look at this first one. We're going to look at the limit as x approaches infinity of, say, x plus 1 over 3x squared minus 3x plus 2. Okay, so we're going to see what happens as x goes way out to the right. What does this function do? Okay, does it approach some number or doesn't it? Some of you might remember things from pre-calc, and you might have an idea of what the answer is, which is good. Okay, but let's see how we can arrive at that answer algebraically. So algebraically, as x goes to infinity, what I can do is I look at the highest power of x present, and that's x squared here. What I'm actually going to do is I'm going to multiply the top and bottom of this fraction by the reciprocal of the highest power of x. So that would be 1 over x squared. Now this whole thing, this new fraction I wrote, is what? Just a fancy form of the number 1. And when I multiply by the number 1, I'm not changing the value of this original thing. I'm just changing the way it looks a little bit. So let's see what happens when we distribute. This is going to become the limit as x approaches infinity. So up top, I'm going to have x over x squared plus 1 over x squared. Down below, I'm going to have 3x squared over x squared minus 3x over x squared plus 2 over x squared. Okay? And now I'm going to simplify this. So that becomes 1 over x. The next term is just 1 over x squared. I'll leave that as it is. In the denominator, the first term just becomes 3. Next term becomes negative 3 over x, and then plus the 2 over x squared. Well, look, now what we can do is we can apply this fact up above here to these individual terms. This term, this term, this term, and this term. As x goes off to infinity, those are all little fractions with constants in the numerator, so each of these things is going to approach what? That's right, 0, like we just discussed. And the only thing that's left is this 3, right? That has no x attached to it. That's not affected by what x does, so that stays a 3. Now if we clean this up, what are we getting? We're getting 0 over 3, and what does it equal when we get 0 in the numerator only? 0. So if intuitively you thought that this was going to approach 0, probably because you remember something about where the highest power of x is, then you're absolutely correct. Okay, we're going to summarize this in a couple moments after we get through 2 more examples. Okay, where after we get through these examples, now we're going to be looking at really where is the highest power of x When x approaches infinity, that's often the first thing we're going to look at. Okay, but let's do a second example here. Let's look at the limit as x approaches infinity of 2x squared minus 3 over 5x squared minus 7x plus 9. Okay? Again, intuitively, you may know what the answer is very quickly going into this. If you're thinking 2/5, you're absolutely correct. Let's see why. So again, the highest power of x here is x squared. So I'm going to multiply this by 1 over x squared on top and bottom. I'm going to distribute, and let's see what we get here. So limit as x approaches infinity. So up top, I'm going to have 2x squared over x squared, which is 2, minus 3 over x squared. Down below, when I distribute, I'm going to get 5x squared over x squared, which is 5, minus 7 over x, plus 9 over x squared. Again, we're looking at what happens as x goes to infinity. All of these little fractions where x is only in the denominator, each of those approaches 0. These constants with no x stay. So this limit equals 2 minus 0 over 5 minus 0 plus 0, or in other words, 2/5, which again may be something you knew right away, okay, which is good. We're going to summarize in just a moment. Okay, but again, notice the algebra that's letting us get these. We're multiplying by the reciprocal, the highest power of x on top and bottom, effectively multiplying what we started with by the number 1, so not to change its value, just a way to rearrange it so that we can then apply this big fact as x goes to infinity, get these zeros, and figure out what the limit approaches, okay? All right, so one more example, and then we'll analyze what's going on here. Let's look at the limit as x approaches infinity of 4 minus x cubed over 5x squared plus 6x. Okay? So the highest power of x here is x cubed. So this time I'm going to multiply by 1 over x cubed on top and bottom. Clean that up a little bit. And we'll distribute. So this is going to become the limit as x tends to infinity. Okay, we're going to have 4 over x cubed minus 1 in the numerator. It looks like now 5 over x plus 6 over x squared. And once again, x is going to infinity. All of these little fractions that only have x in the denominator are going to approach what? 0. The negative 1 stays. And look at what we got. We now have 0 in the denominator only. Okay? Which, again, to refer back to our starter problem, that's indicative of a horizontal asymptote, and we should test from both sides to determine the infinity. Well, actually, we can't test both sides of infinity here. So basically, we got to look at the sign of this thing, and it looks like it's negative. We have a negative over a 0. As x goes to infinity, let's see. One thing to be careful of here is let's look at the highest powered terms, right? So like as x goes to infinity, that's going to get really big in the negative direction up top because it's a negative big number cubed. The highest powered term down below is squared, so a big number squared is going to be positive, and that's an indication that we're going to negative infinity here, okay? So, you know, again, the limit doesn't really exist. As we go way out to the right of this graph, the y value is going to shoot down forever. Okay, but what we basically have are 3 cases now for what happens as x goes to infinity. It comes down to where the highest power of x is. If the highest power of x starts in the denominator, if the highest power of x is the same in numerator and denominator, and if the highest original power of x is in the numerator, 3 different things occur. So let's summarize, okay? Okay. So we'll call this 3 cases as x approaches positive or negative infinity. Okay, we got these 3 cases to consider here. Okay, case 1. If the highest power of x is in the denominator, and that was like our first example up here. Notice the highest power of x we began with was 3x squared in the denominator. What did we end up for an answer here? 0. Intuitively, that should make sense. Okay? Forget all this. As x gets bigger and bigger, what's going to grow more quickly? 3x squared, a big number squared, is going to grow a lot bigger than just a plain old big number. In fact, as x gets bigger and bigger and bigger, you know, this minus 3x, this plus 2 become arbitrarily irrelevant to the size of the highest power term. Okay? So the idea is this. If the highest power term is in the denominator is going to grow much more quickly than the numerator. And what effect does that have on the overall fraction? Well, if the denominator is growing more quickly, these fractions approach 0. Okay? So the analytical approach now is to know, look, if I'm looking at x going to positive or negative infinity, I look at the highest power of x. If that's in the denominator, the limit approaches 0 every time. Okay? Second case, if the numerator and denominator share the same highest power of x. Okay, well, that was our second case. We had a 2x squared over a 5x squared, and at the end of the day, what do we get back? 2 over 5. We got back the coefficients of the highest powered terms of x on top and bottom. So the limit will approach the ratio, that's a fraction, okay, the ratio of the coefficients of the highest powered terms in numerator and denominator. Okay, let's try to make sense of those words. The top and bottom have the same highest power, then that limit is going to approach, write it like this, arrow typically means approach, then the limit approaches the ratio of the coefficients of the highest powered terms in numerator and denominator. Okay, it's a lot to say, but it's easy to find. Okay, here, the ratio of the highest powered terms is 2 over 5. Okay? And what's the third case now? If the highest power of x is where to begin? In the numerator. And what happened in that example, this last one? Well, this thing went off to negative infinity, okay? That's what's going to happen. Things either going to grow in the positive or negative direction. So if the highest power of x is in the numerator, the limit will approach positive or negative infinity. We need to determine which, by comparing the signs of the highest power terms in numerator and denominator. It's exactly what we did up here. Highest power up top went to negative infinity cubed, positive infinity squared. We got a negative over a positive. That's what told us negative infinity. Okay? So there's our cases. Let's do like 3 more examples now, or 4 more examples using these more analytic approach here. Okay? So the limit, the algebra up above was just to show you, why we get these results back. Okay? So now let's take a look at the limit as x approaches infinity of, say, x minus 2x squared plus 3 over 1 minus 3x squared. Okay? So again, the idea is find the highest power of x. Well, here we have the same highest power of x in numerator and denominator. And don't always assume the powers are going to go from high to low. On the AP exam, they'll jumble terms up. You got to be careful, okay? But we do have the same highest power, so if we simply compare the coefficients here, we're going to get negative 2 over negative 3, or 2/3. And that's it. Okay, let's look at the limit as x approaches negative infinity of x minus x to the 4th over 1 over 5 plus x cubed. Okay. Again, positive or negative infinity, we'll be careful, but the idea is the same. We're going to look at the highest power of x. Here, it's in the numerator. So automatically, I know the numerator is going to get a lot bigger than the denominator. This thing's either going to go to positive or negative infinity. Okay, we got to figure out which one. Look at the highest powered term in the numerator. Okay, x is going to get big in the negative direction. What's a big negative number raised to the 4th power? That's going to be positive. Then I'm multiplying it by -1. The numerator is going to get infinitely large in the negative direction. The denominator, the highest power term is x cubed. So as x gets big in the negative direction, a negative number cubed comes back negative. So the denominator is going to get bigger in the negative direction. And the overall sign of this fraction, therefore, now is positive. This thing will approach positive infinity at the end of the day. If you graph this and you look way to the left, you would expect the y value to be going up. Okay? But again, analytical approach, focus on the highest power, go from there. Okay, next up, let's look at the limit. As x approaches negative infinity of 3 minus x over x minus 3. Okay? So what do we notice about the highest power of x here? It's the same on top and bottom. So we compare the coefficients. Up top, we have a -1. On bottom, we have a +1. This thing is going to approach -1. Okay, so this thing equals -1. And by the way, you may realize, hey, this like a factor, that's reversed. This in and of itself is reversed subtraction, which is equal to -1. I could have done it this way. This is the limit as x approaches infinity of the constant -1. And since there's nowhere to plug the x, I just get back that constant. Okay? And let's take a look at the limit as x approaches infinity of something like 3x squared plus 2x minus 1 over the square root of 16x to the 4th minus 3x cubed plus 2. Okay? So something a little bit different you're probably realizing right away is that we have this radical in the denominator. Okay? Again, as x goes to infinity, the highest power terms on top and bottom will take over. We can say this is similar to the limit as x approaches infinity of just 3x squared over the square root of 16x to the 4th. Okay? And now we can simplify this. This becomes what? The limit as x approaches infinity of 3x squared. Well, what's the square root of 16x to the 4th? 4x squared. Now we see the powers are the same. This thing will approach 3 over 4. Okay, and limits like these, not uncommon on the AP exam. Watch those square roots and simplify a little bit first. Okay? All right. Now, what's something else that goes hand in hand with limits as x goes to infinity? Well, if you remember from our graph here, as we went to the right or left, we had this blue horizontal asymptote. And in fact, when you're looking at a graph of something, and if there's a horizontal asymptote, where do we get those horizontal asymptotes, right? Typically, it's, as x is going way out to the right, we ride along that horizontal asymptote, or as x goes way out to the left, we end up riding along that horizontal asymptote. So, limits at infinity go hand in hand with horizontal asymptotes. So let's talk a little bit about that. Okay, horizontal asymptotes to the graph of f. If the limit as x approaches negative infinity of some function equals k, or the limit as x approaches positive infinity of some function equals k, where k is a number, where k is some number, okay, some constant, then the line y equals k is a horizontal asymptote to the graph of f. Okay? how many horizontal asymptotes could a function possibly have? Any function will have either 0, 1, or in rare cases, 2 horizontal asymptotes. Okay, there's always 0, 1, or 2. Okay, most have 0 or 1. Okay, but to find horizontal asymptotes, we look at the limit as x goes to positive infinity, look at the limit as x goes to negative infinity. Most of the time, if there's a horizontal asymptote, those left and right limits will be equal. There are rare cases where there could be 2 different ones, though. Okay, so let's take a look at a couple examples here. Okay, so find all horizontal asymptotes to the graph of. Okay, part A, let's say f of x is 5x minus 6x squared over 2x squared plus 3x minus 1. Okay, so to find the horizontal asymptote, we look at the limit as x approaches negative infinity of this thing. And we look at the limit as x approaches positive infinity of this thing. Okay, now what do you notice about the highest power of x? Okay, it's the same on top and bottom. Okay, so it really doesn't matter if x is approaching positive or negative infinity. With this rational function, we're going to get back the same thing. Think about it. In the top case, as x gets big in the negative direction, right? A negative number squared is positive, times negative 6 is negative. A big number squared is positive, times positive 2 is positive. So I'm getting back negative over positive, which, you know, if I just look at the coefficients anyways, that's what we have here. Okay, and we get back what looks to be negative 3 as a value. If I plug positive infinity in the numerator, well, positive number squared is positive times a negative is negative. In the denominator, a positive number squared is positive, right? I'm still getting back this negative 6 over this positive 2. I'm still getting back exactly the same value whether I go to positive or negative infinity. So with rational functions, you're going to get the same value back. It doesn't matter, okay? There's only one horizontal asymptote, and in this case, the horizontal asymptote is the line y equals negative 3. So if we graph this thing down here at negative 3, that's where we would expect, you know, this thing to be kind of riding along that line. All right? But again, rational functions, you're going to have one horizontal asymptote. What if I look at y equals x squared, right? There's a parabola. Limit as x approaches negative infinity of x squared versus limit as x approaches positive infinity of x squared. In either event, these things are going off to infinity. We don't get any sort of number back, okay? So that's an indication there are no horizontal asymptotes. By the way, we know what x squared looks like. That's just our parabola, right? Should be touching the x-axis there. As x goes way out to the right, the y value goes up forever. As x goes way out to the left, the y value goes up together forever, excuse me. And so there is no horizontal asymptote. Okay. And let's take a look at, say, f of x equals the absolute value of x divided by x. Okay, absolute value functions are where we really want to be careful. Okay, and you know, if you want, you can graph this thing and visually find the asymptotes. But a big thing you want to be able to do in this class is rewrite absolute value as a piecewise. Okay, and you've seen me do this in a few lessons. Okay, absolute value of x is positive x. It's whatever that number in the parentheses is, as long as x is already greater than 0. If the number in the absolute value bars is negative, I negate that value to make it positive. This is how we rewrite absolute value of x as a piecewise. Geometrically speaking, here's the line y equals x for x values greater than or equal to 0. Here's the line y equals negative x for x values less than 0. Okay? Well, what I'm going to do is I'm going to take this function and I'm going to rewrite it in absolute value as a piecewise. So here's how this is going to work. The absolute value is in the numerator. Okay? That's where I'm going to apply these characteristics. Notice in the denominator I just have x, but that's not affected by absolute values. So when I go to split this up, that x in the denominator just stays. Where does this thing equal 0? Right at 0. So we're going to have a piece greater than or 0 and a piece for less than 0. And again, when x is already greater than or equal to 0, absolute value of x is just x. So I replace the numerator with x. When x is less than 0, I replace absolute value of x with negative x. And that should make sense, right? It is a positive number. If x is less than 0, like negative 4, what's the negative of negative 4 going to come back? Positive 4. All right, so that's all the bottom is saying is if you start with a negative number, multiply it by negative 1 to make it positive. Okay? And so in any event, I turn the top into negative x. But now this can be simplified. What? Oh, and that's not defined at 0. Careful, this original function is not defined at 0 because of that x in the denominator. Okay, so not continuous at 0. We've got to be careful there. But in any event, look, what does x over x simplify to? 1. F of x is nothing more than the line y equals 1 for x values that are positive, negative 1 for x values that are negative. If I want to sketch the graph of this thing now, at 0 is where it splits. We're up at positive 1 for x values greater than 1. We're down at negative 1 for x values less than negative 1. As x goes way out to the right, what are we approaching? Well, we're approaching the y value of 1. We're always at the y value of 1. So here, the limit as x approaches infinity of this original function equaled 1. And you can also just get it from the piecewise. As x goes way out to the right, we're just always going to be at the number 1. As x goes way out to the left, we're going to be at the number negative 1. Again, you can see that in the graph. As we go to the left, we're down at negative 1. And so there are two horizontal asymptotes, y equals 1, y equals negative 1. Again, this is a rare case. Again, usually dealing with absolute value functions when you're looking at two different asymptotes. Okay, most are going to have 0 or 1. All right. And let's see, one more example here from an old AP exam. Suppose f of x is ax squared plus 3 over bx squared minus 9. If f has a vertical asymptote at x equals 3/2 and a horizontal asymptote at y equals 6, find the values of A and B. Okay, so based on this information, we should be able to figure out what those coefficients of A and B are, okay? So two pieces of information we're given. We're given that f has a vertical asymptote at that x value, okay? So let's think about what that means. When do we get vertical asymptotes? That's typically when what and only what equals 0, the denominator. So we get a vertical asymptote at x equals 3/2. That's an indication that the denominator will equal 0 when x equals 3/2, right? They gave us that value. So what are we going to do? We're going to sub 3/2 in for x, and we can solve for b. So we have b times 3/2 squared minus 9 is 0. Let's see, 3/2 squared is 9/4, so 9/4 of b minus 9 is 0. Multiply by 4/9 on both sides. And it looks like b is going to be the number 4 here. Okay? So we were able to use that piece of information to solve for b. And the other piece of information that we have a horizontal asymptote when y equals 6. Well, that's what we were just talking about. When do we get horizontal asymptotes? By looking at the limit as x approaches positive or negative infinity. And since this is a rational function, I can use whichever infinity. For convenience, I'll use positive. So we know that as we take the limit as x goes to infinity of this thing, we know that's going to equal the y value of 6. That's how we get a horizontal asymptote. So if we're told where the horizontal asymptote is, set up the limit of that function approaching infinity and set it equal to that y value of 6. Okay, let's actually clean this limit up now. Look, as x goes to infinity, what do we focus on? We focus on the highest power of x on top and bottom. That's the same here. So as x goes to infinity, what ratio will this approach? Well, the coefficients give us a over b. So that limit approaches a over b, and we know that that limit equals 6. All right? Now, as long as we know what b is, we can solve for a. We do because we did this bit of work earlier. If we had started with this information, we'd have to realize we can't really solve for a or b yet, and then we'd have to deal with this information until we got one value, okay? But we ended up doing it in a good order. We got b, so I can sub that in. B is 4, and it looks like a then is 24. All right, so a and b, 24 and 4 respectively. All right, and again, just kind of test your knowledge of horizontal asymptotes to be able to set that up.